Good afternoon to everyone. Heat engine converts the input heat into the useful work output. Carnot conceived an ideal heat engine which consists of two isothermal process and two adiabatic process. When a heat engine works reversibly, it achieves the maximum efficiency 1 minus Tc divided by Th. Since it works in a reversible way, the power output becomes 0 since the reversible process takes a infinite amount of time, which makes there is no practical use of the Carnot engine. Therefore, instead of maximizing the work output, maximizing the power output may be the relevant criteria to understand the real heat engine's performance. To do that, compared to the cyclic heat engine, it has the very advantage to consider the steady state heat engine. Steady state engine has a contact with the hot reservoir and cold reservoir simultaneously. It observes the QH dot input heat flux from the hot reservoir and delivers the power output P and ejects the QC dot to the cold reservoir simultaneously. If the piston moves a distance ds against the constant environmental force F, then we can write dW is equal to minus F dx. We can also write the power output using the energy conservation. Now we calculate the entropy production at the reservoir and we rewrite from the definition of the power, and here we separate the rate of change of the quantity and the corresponding conjugate quantity separately. What we mean by thermodynamic force is the one which drives the thermodynamic process, and the thermodynamic flux is the one which responds to this thermodynamic force. When the temperature difference between the hot reservoir and cold reservoir is very small, then and as well as the force fluctuation between the heat engine and environmental is very small, we can write the velocity of the piston and the input heat flux in the linear Onsager relation. We can rewrite the input heat flux as a function of the coupling constant. We get this limit for this coupling constant from the positivity of the entropy production. Again, we rewrite the power output in terms of the force and flux, and we calculate the ejected heat from the first law of thermodynamics. In our calculation, we use the Onsager time reversal symmetric condition. After setting up this basic equation, we study our model. This is our proposed two-stage heat engine. Initially, the heat engine works between the infinite size hot reservoir and finite size cold sink. What we mean by the finite size is that the CV is a finite. So heat engine continuously ejects the heat to the cold sink, so its temperature is keep on increasing, and we assume that after time tau h, the cold sink become equilibrium with the hot reservoir, so we cannot extract any more work. So instantaneously we connect this so therefore it can act as a finite size hot source. This hot source is instantaneously connected to the infinite size cold reservoir, and heat engine starts to work. Since the engine observes the heat from the finite size hot reservoir continuously, the temperature keep on decreasing. We assume that after time tau c, it become equilibrium with the cold reservoir. Then again the finite size sink can come to the initial state, then we can repeat the cycle. In the first stage, the ejected heat flux can be written with using the definition of the specific heat. This is how the finite size effect come into be put in calculation. This work output is become the difference between the time integral of input and output heat flux. Since we assume that the volume of the finite size source is not changing, the total heat gain ejected to the finite size sink is equivalent to the change in internal energy. Therefore, if you want to maximize this work output, we need to maximize the time integral of J2. So we calculate the input heat flux as a function of T and T dot. Solving the Euler-Lagrangian equation for this, the whole term is very difficult. Therefore, we assume that T dot by T is a very small, I mean the whole term is very small compared to 1. We expand up to second order and we write the Euler-Lagrangian equation. Then we find the optimal T dot. From that we calculate the optimized input heat. Here the first term represents the reversible entropy change, the second term represents the irreversible entropy production. This 1 over time will come repeatedly, and here we calculate the work output in the first stage. The second stage is essentially Izumida and Okuda's work, and here the input heat flux as a negative sign, which represents that the hot source temperature is keep on decreasing. Again, the maximum input heat can extracted from the finite size hot sources equal to the change in internal energy, and we get the optimized input heat. Again, we observe that the irreversible entropy production is inversely proportional to the time duration of the process. We calculate the work output in the second stage. And before proceeding the further study, I would like to mention that the two famous model where we get the irreversible entropy production is inversely proportional to time. This is a Brownian particle trapped in a harmonic potential, and this irreversible action is the same in both the cases, isothermal expansion and isothermal compression process. To generalizing this to the macroscopic model, Esposito et al. Proposed that this dissipation parameter with a different dissipation parameter. Here it's a phenomenological constant. They justified this model. Of course, it has a theoretical background for a macroscopic system. And when we have the TH and TC goes to infinite, we recover the reversible condition. Therefore, in our model, for a macroscopic system, we also get this low dissipation behavior for the both input and output heat flux, and we calculate the average power, and we maximize this average power, and then we calculate the efficiency at maximum power. This expression one can see in many models shows the same expression for the efficiency at maximum power. And further analyzing is difficult because calculating gamma is difficult for the general case. So therefore, we consider the near equilibrium linear region, which means that we can take L2 and L22 prime as independent of temperature, and as well as I would like to present for only the symmetric condition, which gives we get the interesting result, and we get the lower and upper bound. How we get the lower and upper bound is that for this condition, the gamma value, the B prime by B, we get a del U by del S. Since the system goes from one temperature to another temperature, this del U by del S can have the limit from Tc to Th. With this only we get the lower and upper bound. For the low dissipation model, this is known as the Carson-Ullman efficiency. We get only the Carson-Ullman efficiency. However, our model shows that we can go beyond this Carson-Ullman efficiency in the symmetric case itself. Further, to understand the nature of the finite system in the efficiency at maximum power, we assume this general form for heat capacity, and we calculate the efficiency at maximum power, and we expand this efficiency at maximum power as a function of Carnot efficiency. We observe that the alpha comes only in the fourth terms. Therefore, the heat IMP weakly depends on the system's property. And one can here I would like to show that one can ask the question that why not the heat engine operates if it is operates between the infinite size reservoir, what the efficiency can be. The maximum efficiency we can achieve is only the heat RC by 2. When we add the additional finite size system, then we are able to go beyond this linear limit. So we derive the low dissipation model for a macroscopic heat engine, and the dissipation parameter can be calculated within the theory. For the symmetric case, we get the lower and upper bound for the efficiency and maximum power, and this Kurtson-Urban efficiency become the lower bound for the symmetric case. And we have also shown that the efficiency maximum power can be increased with additionally using the finite size system, and also the eta MP weakly depends on the system's parameter, system properties. Sorry. I thank Isar Mohali for financial support, and thank for your attention, and I also thank the organizer for giving this opportunity. Thank you.